Section 4.5, Modeling. The goals of this section: know the different types of mathematical models. We're not going to go through all of them in this class, but we will hit some of the main commonly used ones. We want to use the correlation coefficient. This is going to tell us how well our model fits the data. We're going to use technology to create models for data sets. And in this video, I'm just going to focus on using Desmos, because Desmos is free. Everybody has access to it if you have the internet. And it's a really, really easy to use program overall for doing this thing. And then last but not least, be able to answer questions using the models. So the whole point of creating a mathematical model is to use it to help answer questions about whatever it is you gathered data on. So it's really useful to help answer questions, and that's what we're going to put into play here. All right, some models. Overall, we saw some models in previous sections. We looked at the linear, exponential, I even saw the logistic, looked at some of those different things. But in this section, we're going to expand the number of models to include the following options. And there are others, as I said, that are not covered in this course. So linear, this one uses the form, oops, get that out of the way, y equals mx plus b. So that's the common linear equation form. And the basic graph shape is a line. And if you were to look at this on a little graph, you would see just some sort of straight line. So that's the first type of model that we might use in here. Exponential, another one that we used earlier on. There's really two different forms for this. You get the y equals a times b to the x power, or we can use this y equals a times 1 plus r in the parentheses raised to the t power. And the basic graph shape is going to be something like this. If you have b greater than 1 or r greater than 0, you're going to see a graph shape something like that. Or if you have this b in between 0 and 1, or the r being less than 0, you would have a shape something like this. And the first one would be exponential growth, the one on the left. You're going up as you go to the right, exponential growth. On the right side, this graph is exponential decay. As you go to the right on the x-axis, you get smaller for y value. So you have exponential growth or exponential decay depending on what the data is telling you. All right, and then next one here, logistic. We also looked at this one a little bit earlier, and this is the y equals the m divided by this whole 1 plus k times e to the negative c times x power. And the basic graph shape of this, you have something that kind of starts out looking exponential. You see this thing growing up, but then it reaches a point where it flattens out and approaches that m value, the carrying capacity value. So when you look at your scatter plots that we're going to be using to help determine which model to use, if you see something that starts out exponential, always take a look maybe a little later on and see if it starts to curve like this one does and flatten out again. If it does, then you're probably going to want to use the logistic model instead of the exponential. All right, and then some new ones that we haven't really seen before but are going to be used in this section. The parabolic. We have the form here, y equals ax squared plus bx plus c. So this is what they would call a quadratic form, or it gives you a parabola. So you might also see this as a quadratic. And the shape of this is going to be some sort of U shape. So It might be facing up, opening up, could be opening down, but the idea is that the data has a distinct U-like shape to it, and then you know it's parabolic or quadratic. The cubic. So a cubic is going to be something where you've got this y equals ax cubed plus bx squared plus cx and then plus d. So the highest power, or the degree as they call it in different circles, is 3 for the cubic. And what you see with a cubic graph is going to be something like this, where the shape kind of goes up and then flattens out and then keeps going up. In a sense, you can think about it like somebody took a parabola, one half of the parabola, and then just bent it over the y-axis, or x-axis I should say, reflected it over and created this new shape for the cubic. So it's not exactly the same as a parabola, but you can kind of visualize it like that. Like you took this and it's like, oh, well, we just kind of flipped this over here, and now it's got some parts down there on the negative side and on the positive side. One way that you might describe this too is maybe like some sort of lazy S type shape, but at any rate, you're going to see something like this if you're going to use the cubic model. And then last but not least, we have the periodic. And for what we're going to do with periodic in this class, we're going to use the form y equals a times sine of, and this is multiplication there, of bx plus c and then out back plus d. Now we don't do trigonometry in this class, but if you are noticing that the data is cyclical, periodic as they call it, you're going to see something like this, where the data goes up, comes down, goes up, comes down, goes up, and just keeps, repeating that cycle of up then down, up then down, up then down. And if you were to look more into trigonometric functions, this sine function is one of the many different trig functions, but it's one of the better ones to use in terms of the periodic stuff. The cosine is the other, but if you know a lot about trigonometry, and in this class there's no expectation that you know anything about trigonometry, sine and cosine are really closely related if you just shift them left or right. So they just go ahead and use sine, and just know that it's a trigonometric function that helps you model periodic things. We won't be doing anything more with that type of function than this. Okay, so the correlation coefficient, let's take a look at that. We have our 6 different models that we are going to put into play in this class, and after you plot the data in a scatter plot and examine the scatter plot, the correlation coefficient can help with choosing an appropriate model. And there is going to be some trial and error with this, so don't get discouraged, and don't maybe stop at one. Maybe try a couple if you're unsure. Oh, is it exponential or logistic? Maybe try a couple of different ones. Some of them are a little clearer, but sometimes the data, it's like, well, it could be exponential or linear. It looks close. And this correlation coefficient can help you choose the appropriate model. And basically, excuse me, the correlation coefficient is denoted by r squared, and it can be used to help determine if a model is a good fit. So the value r squared represents the proportion of variability in the data that is explained by the model. So, for example, if r squared is 1.0, the highest value you can get for this correlation coefficient, then the model can explain 100% of the variability. And basically what you would see is that the model will go through every data point perfectly. Nothing is left out. It goes through it perfectly. and it's a perfect fit. So all of the variability that you see from going point to point to point can be explained by the model. The model will predict it perfectly. Now, however, if r squared is 0, the lowest value you can get, then the model doesn't match up with the data at all. There is none of the points are on your model's graph. Nothing is lining up right, and the model does no job, no good job really at predicting what the next point will be as you move along. So most of the time, your r squared is not going to be 0 or 1. It's going to be somewhere in between. And if we take a look here, just like an example here for r squared is 0, I'm going to draw one over here. For r squared is 1, just to kind of show you visually what this might look like. So let's say we had some scatter plot points that look like this. And it's like, well, that looks like a straight line. Then you put your linear model into play with the data, and the linear model is a perfect fit. Hits every point. And that's what you'll see when it's 1.0. Now, with r squared equals 0, what you're typically going to see with this a lot of times is something where, like, the data points, and I'm drawing these even a little bit more organized than what they might be, but I want to try and make sure that what you're seeing here is basically like a blob of points with no real shape to it. And if you were to try to put a linear model through this, you can't fit it. It's not going to hit any of the points really that good. You might hit a few, and I've got them lined up more here than what I really want to have. But the linear model will not predict the data variability at all. It won't help you predict a y value from a given x value, so to speak. And it is hard to get a 0 out of this. There's usually, like, you'll try and fit in, you might get a really low number, but theoretically, this thing, if it's a 0, it's not going to predict the data variability at all. It's not going to work at all. So usually, if you're asking, well, what's good? 1 is perfect, 0 is terrible. What's good? What's a good r squared? How do I know if this is an okay fit? So usually r squared above 0.5 is an okay fit. You should always visually inspect the model's graph, though, before making any final decisions. And what you're going to do in this class is, maybe if you're unsure, try a couple of models and compare the r squareds. The higher the r squared, usually the better the model is for predicting the variability, and it should fit the data better. Now, as I said, you should always visually inspect it, because sometimes maybe there's a little weird quirk in the data, and really it's overall it's linear, but there's one little part that makes it seem like, oh yeah, this thing's actually exponential, and you start plugging them in. Maybe the r squared for the small amount of data that you have is actually going to tell you, oh, you should be using exponential. But really, the eye test, it's like, well, no, there's just like a couple of weird glitches there. It's really more linear if you look at the beginning and end, so to speak. So, you always want to visually inspect this, and it's even more true when you have smaller data sets. When you start getting lots and lots of data values, the trend is kind of established. But with smaller data sets, sometimes you almost want to overrule the r squared based on what you see to pick a proper model. Okay, so what we're going to do now is stop part 1, and I'll pick up with the technology in part 2.